Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 12, Lesson 5 on independent events. This is our final lesson in probability and it's really quite an important one. It's the idea that we could actually look at two events and ask ourselves, are they independent of one another or are they non-independent of one another? So let's jump in and really try to understand what we even mean by that. Independent events. In a previous lesson, we saw how the occurrence of one event could change the probability of another event. That was what was known as conditional probability. When this happens, we say that the two events are not independent of one another. When the occurrence of one event has no effect on the probability of another event happening, we say that the events are independent. Now, a lot of times it's very easy, in sort of a theoretical probability perspective to say, sure, these two events are independent or these two events are not independent. All right, so let's take a look at that scenario in exercise number 1. Classify each of the following scenarios as having events that are independent or not independent. Letter A. A person pulls a red marble out of the bag that has 5 blue and 7 red marbles and does not replace it. Then a person pulls another red marble. Is the probability of pulling the second red marble out independent of pulling the first red marble? Explain. So again, I want you to think about this. Is the probability of pulling that second red marble out independent or not independent of the event of pulling the first red marble out and not replacing it? Pause the video now and consider that. All right, well the key here is the fact that we do not replace it, right? We do not put the red marble back in, okay? And therefore these are not independent, right? And again, the key is to really just consider this, right? When I pull that first red marble out, right, the probability of pulling it out is, well, there are 7 red marbles out of 12, so the probability is 7/12, right? But when I pull out the second red marble, because I haven't put the first red marble back, now there are only 6 red marbles left. There's only 11 total marbles left. And so the probability is now 6/11 that I'll pull the second red marble out. So it's not independent because the probability of pulling the second red marble out, and I'll just say the second out, changes because we don't replace the first. Now you could see the scenario though, right? Where I pull a red marble out, the probability of doing that is 7/12, and then I drop it right back in the bag. And then pulling that second red marble out is completely independent of pulling the first one out because the probability is still 7/12, right? Nothing will have changed. Let's take a look at scenario letter B. A person flips a coin and notes that it comes up heads. Then the person rolls a standard 6-sided die and notes that it comes up as a number less than 3. Is the probability that the number came up less than 3 independent of getting a head when flipping the coin? Explain. All right, well, pause the video now. And is getting a number less than 3 independent or not independent of flipping that coin and getting a heads on it? Well, in this case, it's definitely independent. All right, and it's independent because no matter what happens on the coin, the probability of getting, let me extend this, less then a 3 is 2/6, right? Doesn't matter, right? I could flip the coin 20 times and get a heads each time. And the probability of getting a number less than 3 when I roll the die is going to be 2/6. It just doesn't matter, right? And because the probability doesn't change for that second event, right, based on what happens in the first event, the two events are independent of one another. Now, in these two cases, it's pretty clear. We've got two events that are not independent here because the probability of the second one happening changes depending on what happens with the first one. Whereas in the second case, they are independent because the probability of the second one happening has nothing to do with the first one happening. So let's take a look at a situation where it's a little bit more complicated. Let's call this testing for independence. The idea of independence of two events is one that kind of comes naturally, right? And is very important in seeing if there's an association between two events, especially when we start looking at empirical probability. We're going to stick with theoretical probability here in just a bit. But let's develop a tool to test for independence. Exercise number 2. The spinner below is spun once and its outcome is noted. Let E be the event of getting an even, let P be the event of getting a prime, and let L be the event of getting a number less than 5. Find the following probabilities. All right, before we start launching into all the probabilities, let's just be very clear about all the sets that we have, right? And let's kind of list them out really fast. We'll just kind of do them up here, right? We've got E is the event of getting an even. So let's write that out in roster form. So E would, of course, be simple. Those would be the numbers 2, 4, 6, and 8. All right. P is the event of getting a prime. Those are the numbers 2, 3, 5, and 7. And L is the event of getting a number less than 5. So that's 1, 2, 3, and 4. Right? So those are all the events that I'm thinking about here. All right, great. So first thing first, very easy, letter A. Let's find the probability of getting an even. All right, well, you shouldn't need any help with this. Why don't you go ahead and do that? Now, I hate to be really formalistic about it, but I'm going to be, right? The probability of getting an even is the number of events that fall in my even divided by the number of events or outcomes that fall in my sample space. So that's obviously 4 that lie in even. There's 8 total, 4/8, and I'm going to actually reduce this down to 1/2. So the probability of getting an even when I spin the spinner once is 1/2. Awesome. All right, but now let's start getting into some conditional probability that we worked with last time. So let's take a look at letter B. The probability of getting an even given that the outcome was a prime number. All right, well, we talked about conditional probability last time, so what I'd like you to do is go ahead and try to figure that out. Now remember, once we say that we're getting an even given that we have a prime number, that means that our sample space suddenly becomes this, right? Our sample space is no longer 1, 2, 3, 4, 5, 6, 7, 8. Now our sample space is 2, 3, 5, and 7 because I'm telling you, right, that you've gotten a prime number. I've spun the thing around and I've definitely gotten a prime number. So the probability that I've gotten an even, given that I have a prime number, well, there are 4 prime numbers and only one of them is even. So the probability there is 1/4. Now notice, before we even move on, how much lower the probability is of getting an even given that we got a prime number than just getting an even if there's no restriction at all other than the overall sample space, which is that I got a number between 1 and 8. By the way, that's a condition all on itself, right? I mean, if I just said, what's the probability of getting an even number? Well, that's a tricky one to talk about, right? If you don't know what the sample space is at all. Really, this is what is the probability I got an even number given that the numbers that I pick are integers between 1 and 8 and inclusive. But we don't say that. We just have our sample space sitting here. All right, so now let's take a look at letter C. The probability of getting an even given that the outcome was a number less than 5. All right, well again, keep in mind right now our sample space is 1, 2, 3, and 4, right? That is now our sample space. So why don't you pause the video and tell me what that conditional probability is. Okay, well now this conditional probability says the probability of getting an even given that we have a number less than 5. Well, there are 4 total possibilities in our sample space. 2 of them are even, and so that probability is 1/2 again. So now let's take a look at letter D. Which event, P or L, prime or less than 5, changed the probability that E would happen? Which did not? Well, this should be pretty easy. Why don't you go ahead and take a look at our answers to A, B, and C, and you should be able to answer D pretty easily. Well, P, right? P, getting a prime, changed the probability of getting an even L, right, less than 5 did not change it. And that really is the crux of independence, right? That means that getting an even is independent of the event L, getting a number less than 5. Because whether or not I don't restrict my sample space, or whether I restrict my sample space to just being L, the probability of getting an even remains 1/2. On the other hand, the probability of getting an even, or the event of getting an even, and the event of getting a prime, those are not independent of each other because getting a prime lowered or changed, more importantly, changed the probability that I got an even. Okay? And that really gets to the heart of independence. So let's now talk about that. The definition of independent events. 2 events, A and B, are defined to be independent if the occurrence of one does not change the probability that the other one happens. In formula form, the probability of A given B is simply equal to the probability of A. And likewise, the probability of B given A is equal to the probability of B. So in other words, in our last particular problem, we saw that the probability of getting an even given that we had a number less than 5 was just equal to the overall probability of getting an even. And therefore, we could say that those 2 events were independent. On the other hand, the probability of getting an even given that we got a prime was not equal to the overall probability of getting an even, and therefore we would have said that those 2 events are not independent of each other. Now, in a theoretical sense, we use the test for independence here and there, but it's actually used all the time in an empirical setting. And before we launch into exercise number 3, I just want to mention, right, if you've ever watched election coverage, especially presidential election coverage, you will oftentimes see tons and tons of this type of analysis on TV, right? Because they'll say something like, exit polls showed that 45% of all people voted for candidate A, but when we look at just men, 52% voted for candidate A, and when we looked at just women, 40% voted for candidate A, right? And what they're doing there is that they're showing, right, that the probability of a person voting for candidate A is not independent of the gender of the person. Whereas they might then break it down along racial lines, let's say people of color or African Americans versus Caucasian Americans, and they might see that the percentages there don't change, in which case that they would say that the probability of voting for candidate A is not or is independent of the racial breakdown, right? And they do that all the time. They break down things for age, for gender, for race, for sexual orientation, right? Because they really want to see, well, what different groups, does this candidate appeal to, and what different groups do they not appeal to? And which ones, it doesn't really matter, right? Because they break down, let's say, evenly. All right, let's take a look at an analysis that's somewhat similar to that, but having nothing to do with politics, I hope. Exercise number 3. A survey of 57 sixth graders was done to determine which subject was their favorite. The results are shown in the table below, sorted by gender. Now, I know that we're all surprised that basically everyone, all 57, didn't vote for math. I get that. You know what I mean? But I had to make this, I had to have some math in it, so I couldn't do that, even though that's probably more realistic. So let's take a look at letter A. Does it appear, based on the data in this table, that the preference for math as a favorite subject is independent of the student's gender? Show the analysis and explain your findings. Okay, great. So here's how we're going to do anything like this. The first thing I want to know is I just want to know the overall probability that a person would prefer math as their favorite subject, right? So the first thing I'm going to do is I'm just going to find the probability that they prefer math. And that's easy enough, right? There are 18 total people that prefer math out of 57. So I'm going to just do 18 divided by 57. Now, it's hard to compare fractions. We all know that, right? The only way to really properly compare fractions is to have common denominators, which we're not going to have in this particular problem. So we need to go with decimals. And if you're going to go with decimals, you should just go with a 2-decimal place variety here, because we're talking about things that really are equivalent to percentages. So I take my calculator out, I work out what that is, and I find that it's about 0.32. In other words, in the population as a whole, about 32% of all the respondents of this survey said that math was their favorite subject. Okay, so now what we're going to do is we're now going to look at the probability that a person liked math as their favorite subject given that they're male, and also given that they're female. All right, so let's take a look at the probability math given male and the probability of math given female. Now what I'd like you to do is I'd like you to pause the video right now and see if you can do these two empirical probabilities on your own, and also then think about what the answer to the actual question would be, and then we'll discuss it. Pause the video now. Okay, now this is kind of cool because as soon as we're looking at the probability that a person likes math as their favorite subject given that they're male, right, conditional probability, all I'm doing is I'm saying in this situation I'm only going to look at this row of the table, right? Now there are 27 total, I kind of wrote right through that, and of those 27, 10 of them like math as their favorite. So in this situation that's going to be 10 out of 27. And that's going to be for about 0.37. Now, side note, right away, this is enough to say that there is not independence, okay? Because the probability that you're going to like math if you're a male is different, in fact, higher than the probability that you're going to like math overall. Side note, that should mean that the females are going to be actually lower than that because it's going to somehow balance out to be 0.32. But let's also do that particular calculation. So in that, right, we limit ourselves to just those who identify as female in this, which is going to be 30 total. 8 of them prefer math as their favorite subject. And that ends up being 0.27, right? Now, because these two are not the same as that, or even because they're not the same as each other, that's another way to look at it, we can say that there is some kind of an association, right? It's not independent. So I'm going to say that no, not independent, because the probability changes Probability changes depending on gender. Oh, it just fit in. All right, and that's exactly the kind of analysis that people do all the time. Now, don't get me wrong, right? There's probably a lot of different reasons for that, and then statisticians would want to dig in and try to understand what is it about math, that potentially makes it a less likable subject for people that identify as female versus people that identify as male, right? There might be historical reasons for it. Maybe they'll even track these numbers over time, all right? But right, you would first want to see if there is that association, and there's most definitely an association in this particular data set between a preference for liking math and self-identified gender. So now let's take a look at letter B. Does it appear, based on the data in this table, that the preference for social studies as a favorite subject is independent of the student's gender? Show the analysis and explain your findings. All right, well, what I'd like you to do is pause the video now and go through exactly the same analysis we just did, but for social studies instead of math. All right, so first thing I'm going to do is I'm going to just figure out the probability overall of social studies. I'm just going to abbreviate that as SS so I don't have to keep doing social studies. Again, what we've got is we've got 19 out of 57 overall. And if I do that on my calculator, I find that it is 0.33. Then I'm going to look at the probability of social studies given that a student is male. All right, in that situation, we're looking at 9 out of 27. And that ends up being 0.33 again. And now the probability of social studies given female, and that's going to be 10 out of 30, and that ends up being 0.33. Now think about that. What that is telling you, right, is that regardless of whether the person identifies as male or identifies as female, 33% of them like social studies as their favorite subject. And therefore, the preference for social studies as a favorite subject is independent of the person's gender. It doesn't depend at all on what gender the person is. So in this case, we'll say independent because the probability does not change with gender. And again, one might actually say, well, what is it about social studies then that makes that true? What is it that makes it so that about a third of all respondents, or actually in this case exactly a third of all respondents, regardless of being male or female, prefer social studies as their favorite subject, right? What is it about that? And maybe even more to the point, right, how can we then get more females to like math as their favorite subject? And again, I know it would be more like 90% like math, and then the other 10% would be split up in some random way amongst the other 4. But, I had to make up a problem somehow. Okay, so let's look at one last thing having to do with independence. Now, I really like the discussion that we just had. But there's another test for independence that I don't think is nearly as intuitive, but we oftentimes like to show because it's a very quick test for independence. And it's what's known as the product test for independence. There's a nice test for independence that can be applied easily and comes from our formula for conditional probability from our last lesson. So let's develop the formula and then use it. But I do want to keep in mind that generally this is sort of a shortcut to the analysis we just did. Does it work? You bet it does. But I don't think that it's as great of a feel. So let's talk about it. Exercise number 4. Given that the probability of A given B is equal to the probability of A and B divided by the probability of B, do the following. If events A and B are independent, then write this formula and solve for A and B. All right, so in other words, this is the formula that works for finding a conditional probability in every situation, whether the two events are independent or not independent. Okay, it always works. But if we have independence, right, independence then implies that the probability of A given B is just equal to the overall probability of A. That's literally the definition of independence. The probability of A given B is just the probability of A. So I can take this formula, which always works for conditional probability, and say, well, if the two events are independent, then I'm going to replace probability of A given B with just the probability of A. All right? So this formula will always be true for two independent events. But now I could multiply both sides of this equation by the probability of B, and I could find that the probability of A and B is equal to the probability of A times the probability of B. And this, let me put it in red, is a nifty little test for independence. In other words, right, if we know the probability of A, right, and we know the probability of event B, and we know the probability of event A and B occurring at the same time, if this product is equal to this one, then the two events are independent. If it's not equal, the probability that the two events are not independent. Now, the thing I don't particularly like about this is that it really gets, you really kind of forget about this piece. This piece doesn't show up at all, so you don't really have that sense. But it is a very fast way of telling whether or not two events are independent or not independent. Let's take a look at an application of it in letter B. The probability that a person is left-handed is 12%, which is true. The probability that they have brown eyes is 42%, also pretty accurate. The probability that they have brown eyes and are left-handed is 2%. Is the event of having brown eyes independent of being left-handed? Support your answer. Okay, well, if the two events, being left-handed and having brown eyes, are independent of each other, then when I take these two probabilities and I multiply them together in their decimal form, I should get this particular probability in its decimal form. So let's take a look, and let's kind of like lay it all out, right? We've got the probability of being left-handed is equal to 0.12. The probability of having brown eyes is equal to 0.42. And the probability of being left-handed and having brown eyes is 0.02. Now again, if they're independent, right, then when I take the two individual probabilities and multiply them together, right, the question is, does P of L times P of B equal P of L and B? All right, well, let's do it, right? It's very simple. 0.12 times 0, that doesn't even look like a 0 now, it looks like a theta, 0.42. Does that equal 0.02? Well, it's simple enough to take our calculators, type in that product. What we find is that that product is equal to 0.0504, which does not equal 0.02, which tells us that they are not independent. All right, if they were independent, then the products would be equal. They aren't. So not the product, but this product would be equal to that one. They're not, so they're not independent. And again, people love the product test for independence because it's very quick, right? But what it does is it starts to sort of, in my personal opinion, it starts to sort of lose the sense of what makes two events independent. This whole idea that the probability of one occurring changes the probability of the other one occurring. And you don't really get that feeling for this. You don't even get a feeling for how sort of like one occurring has changed the probability of the other one occurring. You just know that when you do the product of the two individual probabilities, it doesn't equal the product of their intersection, right? The and situation there. But it does work, and it is fast. I would still suggest that any time, especially that you're dealing with an empirical situation like this, you go with this test. You know, check what the overall probability is, then check what the individual sort of like conditional probabilities are. If those conditional probabilities have changed from the overall probability, well, then you've got not independent. If they remain the same, as we saw in letter B with the social studies situation, then they are independent. All right, let's wrap this up. Let me see if I can find the end slide. All right, so independent events are actually one of the most used thing in all of probability. As I mentioned, like watch election coverage sometime and see how they break down, right, election results based on all of these conditions. The person was a male, the person was a female, the person was, straight or gay, the person was, African American, Caucasian American, Asian American, etc., right? They're going to break down the results in all sorts of ways, and every time they do, right, they're always finding the probability that a person voted for candidate A given that they are male, or given that they are African American, or given, right, something, right? They don't phrase it that way, but that's what they're really doing. And they're always looking for that dependence, right? They're looking to say, well, if you fall into category X, then you are more likely or less likely to vote for candidate A, right? And they're always kind of looking for that dependence. And it's not just politics. There's all sorts of things that they're looking for, right? So, if you drink, water with fluoride in it, are you more likely to get cavities or less likely to get cavities than if you don't drink water with fluoride in it? Are those independent events, right? Or is there some kind of dependence or correlation there, right? So, that's why we talk about probability in terms of independent events and in terms of conditional probabilities. All of this actually segues nicely into our next unit, where we're going to start to look at statistics, and we're going to start to look at how we can make inferences about populations and things that happen in our world based on sampling and experimental studies that we do. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.